Hello. Remember in the previous lecture, we went through methods on solving linear differential equations that are first order. So generally, we can write them as dy by dx is equal to f of xy. Okay, so that was the most general form of a first order differential equation. Yeah, and we looked at methods of solving this with pen and paper. However, in some cases, that might not be possible. So we resort to numerical methods to solve it on a computer. Okay, so recall that this dy by dx can be approximately written as a quotient. Okay, so using the numerical methods we looked at previously. So we can write this as y of x plus h minus y at x divided by h. And this is approximately equal to f of xy. Okay, so what we can do now is multiply both sides by h. So we get y of x plus h minus y of x is equal to f of x and y times h. Okay, then we can take the y of x over to the other side, and we get y of x plus h is equal to y of x plus f of xy h. Okay, so what we have here is a method for calculating the next y value. So y of x plus h, so the next y value, given the previous y value, and the right-hand side of the differential equation, the dy by dx is equal to this. In other words, given the gradient, because this function f is just the gradient, right? Because it's equal to dy by dx. So this is the gradient. Okay, and if we have the gradient multiplied by our step, that gives us the difference in the function value. In other words, the previous function value plus the step in the function value gives us the next function value. So this is the gradient times the step. Okay, so we have a very simple updating procedure that we can use to build up our function given some starting point. So given our f of xy and some starting point y of 0, so that's our beginning point, and then we repeatedly add this gradient times the step. We repeatedly add that to get the next y value and then the y value after that. So given f of xy and y naught, we can repeatedly add the step, or the gradient times the step, to get the next y values. Yeah, and then we just repeat this procedure, and we can go for as long as we need to. Okay, so this very simple approach is called the Euler method, okay, for solving differential equations. Okay, so the simple method is called the Euler method. Okay, so this is the method written out, but what we would like to do is do it computationally. So we'll do an example to see how do we convert the mathematical problem of solving for y into a computational problem of solving for the next y value. Okay, so let's have a look at an example here. So example. So let's say we have dy by dx is equal to xy squared plus 1. Okay, so we've got this here. You can try and solve this using the previous methods, and then you can compare your results to what we get computationally. But let's try and do this computationally. So since we're writing a Python program, we're going to be using some maths here. But in this case, we don't have any advanced functions like square root or tan or any trig functions like that. So we don't really need the NumPy math library. Okay, but if you want to just get in the habit of importing NumPy at the start of your programs, that's fine as well. Okay, but in this case, we won't be needing it. Okay, but if you want to, you can have import NumPy as NP, okay, but we won't be using that in this case. Okay, so first we need to define a function of this right-hand side, this x times y squared plus 1. Remember, that is our f of xy. Okay, so we can define the function quite easily. We define the function with def, or define f, and it takes two arguments, x and y. And we want to return this xy squared plus 1. So we can simply return x times y squared plus 1. Okay, so we've got our function. Now we need a starting point, our y naught. Okay, because let's say we want to solve this on some interval 0 up to b, for example. Okay, so we start from 0 and we want to go up to this value b. Okay, so we need to know the starting value of the function. We call that an initial condition. In other words, when x is 0, we need some way of determining y. Okay, so in the previous examples, we left that as our integration constant, the plus c. So given an initial condition, we can then solve for that. Okay, but here that's going to be provided by the user. Okay, so our y naught is going to be provided by the user. So it's going to be float input, and then we can just say y naught as our prompt. Okay, so we prompt the user to input some y naught. Then that input, which will be a string, is converted into a float and saved into our y naught variable. Okay, next we need some sort of step size. So here in the beginning, we called it h. That's up to you to define. So usually it's a very small number. So let's say h is equal to 0.001. Okay. The smaller the step size h, the more accurate your answer is going to be. So you can have a go at changing this h and see what kind of changes you get. Okay, so now we need the updating procedure. So what we want to do is start at x being 0, because that's our starting thing here, and iterate from x equals 0 to x equals b, because we're going up to that upper bound. And as we go through, we're going to add the step size. So we're going to start from 0 and go up in steps of h, okay, until we reach our point b, which is also provided by the user. So let's get that. So b is equal to float input. Let's just call it b as our prompt there. Okay. So now we need to update our x. So as we move along x, we can then calculate the y values. So like I said, it's going to start from 0. So let's define a variable x that's going to be 0. Now we want to update until we get to our end point of the interval, which is b. So while x is less than b, we want to update. So we can use a while loop. So while x is less than b, we want to do our updating. So first, let's print out our current state. So that's going to be the current x value and the current y value. So print whatever x is and whatever y is. Okay, sorry, let's just squeeze that in here. X equals 0, and y is going to be y naught. Yeah, we need to start off somewhere. So print x and y. Then we can do our updating procedure. So x is going to be updated by our step size. So x plus equals h. So that updates our x. And then we need to update our y. Remember how we do that? We take the previous value of y and add the gradient times the step. So we can do that here. Y plus equals, so that updates it. So it takes the previous value and adds onto it our f of xy times h. Okay, so that updates our y value. So this program just prints it to the screen. So it starts from x equals 0 and y equals y naught. Updates it until we reach our upper bound b, and then we just get a list of the values. Now, if we want to represent this graphically, we would need to store these values in a list, and then we can use the pie plot to display this. So just as a note here, if we want to display this graphically, we would need to store the XY values in a list. To plot later. Okay, so there's a few things that we would need to add. So we have already gone through plotting functions in a previous lecture, one of the in-person lectures, but I'll just go through that again. So the things we need to add is the import matplotlib.pyplot as plt. Then in our updating while loop here, whenever we print out our results, we could just store them in a list. So we create our x values, y values list, for example. So x values list, y values list. And then inside the while loop, you would then have x values dot append x, y values dot append y. So this is in the while loop. Okay, and then afterwards we can plot this using plt.plot x values, y values. Okay, and then plt.show just to show our result. And of course, you can then add on extra things like labels for the axes, changing the color, all of that. Yeah, but that is explained in the notes as well. Okay, so those are all extra things that you can add. Okay, so this is the rough outline of implementing the Euler method. So we'll just go through that again. So we need to define the function that represents the differential equation. So dy by dx is equal to f of xy. We define that computationally. Then we get our initial y value and initial x value. Okay. So y naught, that's provided by the user. In this case, the initial x value was just 0 over there. Then we can define our step size and our upper bound for x. Okay, so x is going to be within a specific interval, and we get our function values in that interval as well. Okay, then we have a while loop that performs the updating procedure that was mentioned before. So this is our updating process. Okay, and then again, you can either just print the results if you want to look at it as a list of values, or you can add a bit more code and plot the results as a graphical graph. Okay, so that is the Euler method. There is another method that's a bit more accurate, and that is called the Runge Kutta fourth order method. So let's have a look at that implementation. So the Runge Kutta fourth order method. Okay, so it's a bit more complicated than the Euler method, but not too difficult to implement. So again, we are given the differential equation, dy by dx is equal to f of x comma y. Okay, so now we need an updating procedure for y. So we do it in the following way. So just a note. When we have our y of x plus h, I'm going to call this y of n plus 1. Okay. And then y of x, I'm going to call that yn. Okay, because we're going up in discrete steps with a size h. So if I have y of x, I'm going to call that yn. So the nth step as we go through. And then y of x plus h, that's going to be y of n plus 1. Okay, so the reason is all of the x values can be written as some initial x value a plus n times our step size h. Okay, so it's always in discrete steps. So a given y value can be indexed by n. Okay, so just note that. So now the updating procedure for the Euler method was just the previous y value plus h times the function. For the Runge Kutta fourth order method, it's a bit more complicated, but not too much. We have that y of n plus 1. So the next y value is equal to the previous y value plus 1 over 6. And then we have k1 plus 2k2 plus 2k3 plus k4. And xn plus 1 is xn plus h. So that stays the same as before. Okay, so we just add h to get to the next point. Okay, so this k1 through to k4, how are those defined? So k1 is just given by f of xn and yn. k2 is given by f of xn plus h over 2. So we take a half step. So h is the step size, so h over 2 is taking a half step. Then yn plus h times k1 over 2. So we define k1, and then in the process of defining k2, we use k1. Okay, so it has to be in that order. Then k3 is given by f of xn plus h over 2. Again, a half step. And then we have yn plus h times k2 over 2. Again, we use the previous k value to define the next one. And then k4 is f of xn plus h. So now we take a full step in x. And then we have yn plus h k3. Okay, so that's how we define our k1 to k4. And then once we have those, we can update our y values. Okay, so that is the updating procedure. I'm going to leave it as an exercise to implement this updating procedure with the following example or following exercise, because you're going to be doing it. Okay, so write a Python program to implement Runge Kutta fourth order in order to solve. Okay, and then we have the following differential equation. dy by dx is equal to y squared x plus 1. And then we have y0 equals 1. So that's our initial y value on the interval 0, 1. Okay, so our x value starts at 0, and then we're given the initial y value, and x goes up to 1. Okay, so you can either print out a list of the values, or you can use the graphical method to see what the graph looks like. But in either case, please use h equals 0.1, h equals 0.01, h equals 0.001. Okay, so use those 3 different step sizes to see if there's any change in the accuracy of the result. Okay, so that's the first exercise, and then the second exercise. Solve the differential equation exactly. Okay, so we see on the right-hand side here, we've got y squared times x plus 1. We can use separation of variables to solve that exactly. And given this initial condition, we can solve for that integration constant. Okay, so solve it exactly, and then you can compare your results. Yeah, so compare your results with the different h values and see which one comes closest to matching the exact solution. Okay, so that's it for today. The next lecture video won't be on anything new. It will be revision on the quantum mechanics. Okay, so solving for those eigenvalues and eigenvectors, finding the time evolution, and finding those inner products. Okay, so that will be revision for the test next Wednesday. Okay, and please remember that those first few tutorials are due on the Monday. Okay, please look at the time as well for when those are due. Okay, so you're going to have to scan your work and then submit it on the website. Okay, as always, if you have any questions, please just email me and you can visit me in my office. However, I'm not going to be available today, so Thursday or Friday, so you can come see me on Monday. Okay, so if you really need to see me, you can come on Monday, but if you just have a couple questions, you can email me. Okay, So please look out for the next lecture video on that revision.